Hello everyone, welcome to our webinar. I am Maziar, I lead the team behind the Spark NLP library. I'll be your guide today as we explore the new features added recently to Spark NLP 6, especially our new multimodal data ingestion at a scale. We have a lot to cover today, let's get started. A little bit of agenda before we go through this webinar. I'm going to give you an overview of a Spark NLP library, what it is and how it works. Then we're going to focus on the new ingestion sources that we have, and we added recently a data ingestion to the Spark NLP 6. We're going to focus on vision language models or visual language models, as you wish. We call them VLM. And then a little bit of RAG and how it works, and there would be demos and hands-on at the end. All right, Spark NLP. Spark NLP is an open source natural language processing library. It was built on Apache Spark. More precisely, it has been built natively on a Spark ML module. It was first released back in 2017. The idea was to have a unified solution for all the NLP NLU needs. It's been the most widely used NLP library in industry for the last 5 years, and the most accurate, fastest, and the zero code to scale open source NLP library you can find out there to have all the three things at the same time. I would like to congratulate the team and the people in the community that we crossed 154 million downloads on PyPy. And if you look at the scale that we have since we released and how we added features that the community were asking us and needing depending on the time, there is a correlation between what we released and how the community responded by downloading the library. So thank you very much from the team behind the Spark NLP. Now, one of the cool things about Spark NLP is the large ecosystem of pre-trained resources. It offers free and open source pre-trained pipelines and models. They are available on our Models Hub. With the extensive collection, you can quickly implement sophisticated NLP tasks without starting from scratch. Now, speaking of pre-trained models and pipelines, I'm happy to announce today our Models Hub hosts over 135,000 models and pipelines ready to be used with one line of code. Now, Spark NLP has Apache 2 license. It is officially supporting Python, Scala, and Java. It is precisely optimized, tested, and supported to be integrated in Jupyter, Anaconda, Docker, all your tools that you would use normally locally. As in distributed environment like Kubernetes, Databricks, you have your own, I would say, GCP, Azure, and so on. We focus on three principles when it comes to Spark NLP, developing a Spark NLP as a library. First is accuracy. We try to always ship the most accurate solution for any NLP task. The second one is the scalability. Whatever we ship, it must scale, and it has to scale 0 to linear, so you don't have adding 4 nodes and you will see twice faster, right? You want it to see close to 4 times faster. And the speed, meaning that not always have to be in the cluster or in multiple node situation. You want it to be also faster within the single node. That's the three principles that we try to develop a Spark NLP every time we ship a feature. Now, just to show you how easy it is to use a pipeline, we have over 54,000 pipelines ready to be used with one line of code. As you can see, it's just pre-trained pipeline. You put the name of the pipeline. You define whether or not it's the CPU or GPU, and then you, based on what the pipeline does and what's inside, you will see the result of the pipeline. That's how easy it is to use pipelines. It's also easy to use train your own model. Here you can see we are training a name image recognition by using BERT embedding, which was the smallest one, obviously. But even then, after a few minutes, you get up to 90% accuracy. And it's all being done in a Colab notebook with the free resources. You don't need much resources to train NER. And here's embedding at a scale. We talked about how easy it is to be used, the speed, the accuracy. We will also talk about scalability. For instance, As you can see, by natively scaling on Databricks, for instance, here, adding more executors, more nodes, more workers, these are just synonyms, different names describing the same thing. Spark NLP 6 achieves nearly linear speed enhancement. That means the more machines, the more nodes, the more servers you add, the more resources you get. And we could break down the jobs and scale, I would say, linearly. So that was the overview of Spark NLP. Let's focus on the new data ingestion we added in Spark NLP 6. Now, when we set a new era of enterprise scale data ingestion, we weren't actually lying. For the first time ever, we have enterprise focus native support for unstructured and semi-structured data. You have seamless integration, you have native ingestion features that is unified within the same pipeline that you are using. You no longer need any other library or any other dependency to work outside Spark NLP. That means you can distribute that pipeline in a parallel process inside Apache Spark with the same memory optimization, with the same fault tolerance. That means a massive scale, right? Now, what did we add? We have now a Spark NLP reader. Inside a Spark NLP reader, you can ingest and parse multiple formats natively. We'll start with the PDF. That includes your, encrypted bounding box extraction, and etc. You can also ingest Excel with different file extension, obviously. You can ingest PowerPoints, the slides and notes. You can have raw text and logs, including CSVs, emails, and HTMLs. And the use case would be automating, let's say, legal document processing, contracts, filings, NDAs. You could ingest in bulk, have them all together because you know the data is being hosted and restored in different formats, in different modality. It's never in the same thing. Sometimes PDF, sometimes text, sometimes a doc, Word. That way you can extract a structured data from clauses, parties, dates, and so on, right? So that way you can route insights to different contract platforms, CRMs. That's one use case. But obviously, we have many use cases in the industry when it comes to data ingestion at a scale. Now, let's see how easy it is to use PDF ingestion, for instance. We do have PDF to text. You just set the store split PDF to true. That's just one of the options. Spark.read.format binary file will read. All you need to do is to point to the directory where you have all your PDF files. And that's all it takes because these are readers, right? So the Spark NLP reader that we added, I would say natively, it behaves the same way that you had a spark.read. Let's say json.csv.text, right? And that's all it took. And what it gives you once it's transformed, once it tries to extract inside the PDF, you have obviously the text from the PDF. And in one of the examples, if we had time, we will see that you have page numbers. You probably could get even sections. You can get title, right? That will help you easier later to chunk the data coming in, right? Because you would eventually you would like to get these texts, vectorize them, put them in some database, search for them, I would say by text or contextually with the vectors. That way you can find and probably augment your LLM answers, right? We do have a lot of examples how to ingest emails, Excel, HTML, and so on. I will leave a link here. Please go through them. They're very simple, that simple. Now let's talk about vision language models, the VLM, right? Before we go through that, a little bit of a walkthrough what happened previously. We natively integrated Llama CPP into a Spark NLP, meaning we had native support for Intel processors, NVIDIA graphic cards, Apple Silicon chips. That means flexibility to use it anywhere in your infrastructure. Now, for those of you who don't know what Llama CPP is, Llama CPP is an open source project that enables running Llama or any transformer-based large language models efficiently on local devices using C++. and without requiring a GPU. Although you could have a GPU and make it faster. However, it is extremely popular thanks to its amazing quantization feature, meaning that most people are using Llama CPP to get the smaller version of the model that requires less memory and probably performs faster when it comes to inference. Now, that was just local. Scalability and deployment option, since we're supporting all kinds of hardware natively, you could be in a local machine, single node setup, multi-node setup. You can do that in Databricks, Amazon, obviously AWS EMR, Glue, Azure, GCP, you name it. Whenever you have a Apache Spark support, whether it's Kubernetes or anything else, you have a native support of Spark NLP, and since Llama CPP is natively being integrated into a Spark NLP, you have that native support within the library. Now, Spark NLP 6, how does it work? Let's say you would like to load the Llama 3.1, right? That came like 6 months ago. That's how the code looks like. It's not that hard. I mean, you have your text, you have your document assembler, and all you need to do is just load the model, which we call it auto GGF model. You have the name, you have some parameters. We actually have all the parameters because they're native. You can set anything you want. And that's it, 2 stages in the pipeline, and you will get a generation after that, right? Depending on what the prompt is. Whatever the prompt asks, that will be the generation answer. Just to show you quickly how it works with the CPU and the GPU, right? We ran a benchmark 2-3 months ago on Databricks. We chose very cheap GPUs actually, T4. They're not that expensive at all. They're nowhere near A100 or H100, obviously. As you can see, not only the GPU is handling 10 times more load than the CPU, obviously, it also finishes faster, 9 times, I guess, faster, on a very small and cheap T4, I might say. So not only you get what you want faster, you're also saving a lot of money, right, by going to GPU. Here's another benchmark. They highlight several points. One is that the Spark NLP is scaled exceptionally well. Again, with near linear speed up as you add nodes. The scaling efficiencies maintain up to 10, at least 10 nodes, as we can see here, right? I mean, more than that, you need more data. Because as you can see, the time in minutes, I mean, you got to add more data if you want to add more nodes. And both CPU and GPU setup showing similar scaling characteristics, giving users flexibility in their hardware choice. So sometimes you have a Kubernetes on a cluster with a lot of CPUs being idle. Time is not an issue. So you can run it overnight, wait even a couple of hours. So it shows they have the same behavior. The timing might be similar between CPU and GPU, but don't forget GPU again, it handles 10 times more load than CPU. So keep that in mind. Now, that was generative text or decoder-only models. In Spark NLP 6, we have added support for quantized vision language model at a scale, meaning that vision language models today from Llama CPP are now first-class citizen inside a Spark data frame. You can use any quantized GGF models from Llama CPP that can describe, summarize, or reason over visual inputs entirely on premise, offline. You can unblock any capabilities like tasks like image captioning, visual question answering, document analysis, and many more. All within the same familiar code of a Spark NLP, same framework. Let me show you something here. Support for GGF quantized VLM, of course. So you can see you have objects, you have animals, you have crowd, you have also documents. Some of the VLM models, they support something like an OCR. They know how to read the documents and output a structure in JSON or Markdown or simple text, up to you. Now, this native inference at a scale is available in all common platforms, obviously, including GPU acceleration. Now, we're focusing on CPU, but don't forget we do have GPU support, right? That means massively parallel multimodal batch processing across large diverse image datasets. We take all the images, we run them for an hour, we create questions, then we take the question, we run them again, we generate answers, and the answers would be a very complete explanation of what that image is. And then we embed that next to other text material, and then we use it in search. That's how you can search within both written text and also visuals. Now, again, here is a code example. We always try to keep it simple. Again, all you need is image assembler, right? Your document assembler, and a new annotator called AutoGGUF vision model, which obviously you put your vision model there. It accepts two columns. One, obviously your image. The second one is your instruction. What do you want? Here is the image. Do you want it to be summarized? Do you want it to be described? Do you want to ask a question? Because probably you know what the picture is. Where is the man standing? Who is crossing the street, right? Depending on what you're looking for. Here is a small benchmark we ran with this new annotator to make sure everything works properly. On a Databricks G4DN X large, which is also T4 again, we're not using any big GPUs here at all. We just don't believe in that. If we are using a small quantized models, there is no reason to go that big and spend that much money. You can see the number of workers being added. You also have the same similar linear scalability, even in the vision and visual language models. All right, now let's look very quickly in high left of RAGs, right? Or your retrieval augmented generation. I mean, it's 2025. I know everybody knows what it is, but what it means within a Spark NLP today. It means you can have multi-format document ingestion. You can easily process PDFs now, Word documents, HTML, text, and many more. We are committed to add more data sources. We believe in just pointing to a directory and ingesting everything with all the formats. You are flexible in embeddings. We support a wide range of embedding models, whichever suits you, right? And from that on, we are just compatible with every vector database. We have seamless integration in some of them because they have SDK for Spark, and the rest of them, you can just call them from the API they have. They have their own SDK, you can just use it. I think they run an API or HTTP, HTTPS, and that would be it. I will show you an example in the demo. And we are model agnostic, really. Like any model you would use, the vector size or dimension would go to the same vector database. Where we stand in the pipeline, we are before all that. So the PDF, the text, the doc, go into the vector database. We are right in there. We are ingest all your data sources with all the models we have, multimodal, and then we ingest it, insert it into the vector database. And after that, you're on your own, right? You can use whatever you want. Now, there are some challenges when it comes to RAG. It's not that simple. The first is accuracy. How good is your model? So we have thousands of models, and we're adding them every day, whichever is the state of the art. So you would never be stuck into which model you have to use. Some of the platforms, they have their own models, so you're stuck with them. For instance, if you use OpenAI, it has only one embedding model, right? It is what it is. With us, you have the small, you have large, you have medium, you have all kinds of providers. The second one is speed and scale. Let's say you need to ingest 50 million documents. The only way you can do that is to be natively distributed. I cannot emphasize how important that fact is. At the beginning, in some of our AI applications, we try to use other Python applications to ingest that many data. It just doesn't work. You cannot loop through that. You cannot batch through that. It's just impossible. The only way you can do in an enterprise grade ready ingesting 50 million, 100 million documents using these language models, even quantized, they still need compute, I would say reliably, is using Apache Spark and Spark NLP on top of that. Now let's do some demo. I'm excited to show you some hands-on Spark NLP. First, we look into Databricks and Weaviate. Weaviate is a vector database. And then if we have time, I will show you some embeddings on AWS Glue, the latest one that comes out, how we ingest PubMed. Now let's move on to our hands-on, the first demo that we have. I prepared a notebook on Databricks just to show you how the library, the new feature, works in a distributed environment such as Databricks. And I think is an end-to-end example of how you can point to some images, get some text out of them, vectorize those texts, put them in a vector database that is not even remotely here, and then query them back, right? I think that's a very nice example that we have. Now, what do we have here? I'm going to zoom in a bit. Hopefully, this is going to work. Databricks already starts a Spark session, so don't worry about that. What we're going to do is that we're going to point to a folder image sample. I have, I think, around 100 images here. And then I'm going to just read them as data frame, but with the new column. I would like to add instruction. And the instruction for all the images is the same. Explain this image in one sentence. All I need is one sentence, just explain it. Now I'm also adding an ID. So later on, I could match the query coming from Weaviate to the ID of the data frame here. And I'm repartitioning it to 10 because I only have 10 GPUs, 10 nodes, each with one GPU, and they're also T4, they're not that big. All right, so this job is running. It's going to read all the images, get the resolutions, do its thing as a binary, and move on. Let's look at the next block of code before that thing is done. All right. Okay, so this session is started. It's finished. Thank you very much. You get also the display, what's inside, right? So you have a path, you have a modification time, obviously, length, content. These are usually what the pictures look like. They are ImageNet, if you're familiar with the ImageNet. And here's your instruction for all the images, pretty much the same thing. Explain this picture. For instance, this is the bird with the white background. And here's your unique ID randomly being assigned, right? That's what we have. All right, let's moving on to defining our first pipeline. The first pipeline, we have a document assembler to take the instruction, create a document out of instruction. We have our image assembler to take the image and create the image assembler. And then we just simply feed these two into AutoGGF vision model. The model by default is Lava 1.5. The 7 billion parameter, it's quantized to 4 bits, right? So it's a quite big model. So what we expect is an output column called completions. The completion is supposed to be what? Describe this explanation of the image, right? That's what we're looking for. And at the end, we have a finisher just to get the completion out and give us just a string. That's all we need, right? All right, let's go. Pipeline stage is all here. We are fitting it over the dataset we just prepared, transforming it over the same thing. Right here, right now, I'm just going to write it down and read it back. Why? Because, well, we have to process them anyway, right? And I'm moving on from this pipeline. Why don't I just save it on the disk, read it back, so I don't have to come back to it later on, right? All right, this job is going on. You have some visualization to show you how it looks like, the Spark UI. You can see whether or not it's being distributed over all the executors, right? It gives you some DAG visualization, obviously. You have, what I really like is this, because it shows me all the machines, the 10 nodes are involved, and they are crunching the data. It's a good tool to debug, making sure you are distributed and you're not running only on one machine, right? So we are generating description for around 115, and it's finished. All right, it's done. Now I'm just going to read it back. We already read it back. I want to see how it looks like, right? So I need to see a table that has the ID, it has the image, and it has the explanation now. A bird is sitting in the grass with its head turned to look at something. That's a very detailed explanation. Thank you very much. A white PlayStation 3 sits on a table. That's also very nice. A boy and a girl are sitting on a bench, both wearing some bros. the person is feeding a fish. So this is good. It worked. The model took the image. There's a small image coming from ImageNet datasets and just explained it, right? But what do you want to do with this text? I have an idea. I'm going to feed it into the second pipeline. The second pipeline, another document assembler, getting this string completion, and then using an embedding. We have a wide range of embeddings from E5 to BGE, you name it. Anything that's out there, we have it, natively supporting. We also have AutoGGUF embeddings. So if there is a quantized embedding out there, you can just bring it in. For today, I'm using Nomic. I'm getting the string and I'm just outputting vectors. As always, I'm using embedding finisher to just get the array out. And since this is a text, not a sentence, I am just exploding that out. So it's going to be a list of lists. So normally you have multiple sentences. Each sentence has its own vectors, and then you deal with it however you want to deal with it. But in this situation, it's only a text. So I'm just going to flat it out. Again, you have the stages of the pipeline, document assembler, text embeddings, embeddings finisher, now exploding the vectors, which is just a simple SQL transformer. So the thing is done. So embedding results finished. Let's visualize it. Let's see how it looks like. Give me the ID, give me the content, give me the completion string. We already have those. But I'm not looking at the features. What the feature is the embedding, right? This is the embedding coming from Nomic. All right, thank you very much. So what can you do with that? Here's what I'm going to do. I would like to ingest this into a VVet database. A VVet database that is remotely available as a service, not locally installed. So first, I'm going to convert this into Panda, right? Just do a df head, see how it looks like. This is how it looks like, perfectly fine. What's the type? Everything is object, no problem. This is how you connect to your VVet database, right? So you have it, probably this one is in Europe. Yeah, that's the Europe cloud. You have your API key. Don't worry about it. I'm going to remove it after this webinar. And then you have the client connection. Now the client, when it's ready, which is ready, true, what you can do is you can create a collection. Since we're doing this for a demo, I keep collecting, creating it. So I don't want to keep creating a new name. I'm just going to remove whatever is there and create a new one. Now we have a collection called Multimodal rack, right? What I'm going to do is just going to loop through all this and insert them into that database. I'm 100% sure there is a better way to do it, but it's a very small data set, right? And it's done. It is asynchronously going there and putting them there, right? Let's get it, insert many, perfect. And then you fetch some objects. They work, very nice. What I'm going to do now is I'm going to create a couple of questions. And I'm going to run it through the same vector pipeline. Why the same vector pipeline? Well, that's how it works, right? You use a model, let's call it model A, to vectorize the text. And you put it in a database. And then you have some question or you want to search something. You need to use the exact same model to vectorize your question in order to do KNN or context similarity. You can't use any other models. I mean, you could, but you just don't get a good quality return. I had 3 questions. Is there any spider? A group of people, just looking for people, more than one, hopefully. A man with a hat. Let's see what happens. What I'm going to do is that I'm just going to create a data frame, just run it through the same pipeline. I'm going to get a data frame back that has a vector inside, right? If you select the features and just flat it out, I mean, that's how VVet works. You just flat it out, and then you pass that into VVet. So here's what we're going to do. We're going to run it, and we're going to also record the IDs. Why we're going to record the IDs? Because I didn't put the images up there for simplicity. I have the images locally here, right? So here are the question. Is there any spider? It found 2 pictures because we said limit 2. We could have gone higher. We could check for scores. We could remove, have some thresholds. So I printed out 2 images. One is, a spider is on a web in front of some green plants. The spider is on a tree trunk with its legs wrapped around the bark. I don't know what that means really. A group of women wearing hats and shirts pose for a picture. Sunglasses pose for a picture. A man wearing a blue shirt, red and blue stripe. Okay, it seems like we got something, right? And these are the IDs from these things coming back, right? Sometimes they could be the same because you ask for a group of people, it could be a group of men wearing hats, so that could be the answer. Let's filter back and look into the result. See if it makes sense. A man wearing a red blue striped blanket is holding up 2 red hats. We did ask for a man with a hat, right? So you have your spider, that's true. Zoom in. Yep, this is a spider. A group of women, okay, very nice. Another group of women. And then you have a man with a hat, and then you have another spider. So our simplest end-to-end multimodal data ingestion in a remote vector database from a distributed environment such as Databricks worked. If you, instead of 100 images, if you have 100,000 images, a million images, you just add more node. You just make sure your batch size is completely optimized and you repartition your data frame properly so all your nodes are working. And that's how you scale it. Zero code change. You don't have to change any of this code. Now, obviously, this was a very simple example, meaning that if you want it to be more precise, well, what if you go and ask first a couple of questions? Your instruction would be, give me 3 questions about this picture. Like, what would be the question, right? Is the man like wearing a tie? What pants is, what color is the pants of the guy? And so on, right? And then you use this again, you go to the pipeline, and then you use these questions to create a better description and explanation, which would be much more detailed and also lengthier, right? And once you have those details, then your question could be also detailed. Like I'm looking for a red bird sitting on a, etc., etc. So that's one way of going. And keep in mind, the images could be scanned documents. Some models, precisely I would say like Quen or Olmo, these models, they have great capabilities to extract text from documents, tables, charts, and so on. So that was our first demo. A second demo I would like to show you is a AWS Glue job. This one obviously going to be on a bigger scale. So I have a Terraform job here. Nothing fancy. It's a very simple Scala code that reads around 100,000 documents and articles from PubMed datasets that's been sitting on S3. And it's using BGE embeddings, the BGE small, which is a very good embeddings, by the way. If you look at the accuracy versus the ratio to size. And that's all you need in the pipeline. 2 things: to vectorize the text into, any embeddings you want. And it just saves the result back into S3, right? I mean, this part could be anything. You could insert it directly into Viviet, Pinecone, Elasticsearch, any managed services you have on AWS or Azure, anywhere, right? That part is really agnostic. We support everything. So let's see how it works. I do also have a very easy script. And what the script does, while I'm going to actually run it, I do need my MFA code. Depending on your AWS security, you probably need this code. So what it does, it's just going to go use this code, and then it's going to apply an init and apply the Terraform job. And at the end, it's going to ask me if I'm okay with it, which I am. All right. So what the code does really, it starts from here. You put your MFA code, it's going to source them out, export them because I need them in my code. And at the end, it's just going to init and apply. Very simple. Now you should be able to see this job here, right? If it actually worked. Hopefully it worked. It didn't. Oops. One changed. Okay, that's weird. All right, let's try again. We are going to first destroy whatever is there. Make sure there is nothing remaining from the previous demos. All right, done. And we're going to run it again. Now this time, because I've already put the MFA, it's going to check. It's going to check if it's there. It's not going to ask me to put it again. That's a smart. Thank you. Bash script. All right, so now hopefully I'm going to see my job here. Please. Am I in the wrong place? Oh, I am in the wrong place. Sorry. All right, the job was there. I was in the wrong session. Entirely wrong profile. All right, so the job is here. A Spark NLP 6 Scala. And how do we know that? Because if you look at the Terraform, you would see this is also says a Spark NLP 6 Scala. All right, it's on 20 workers. We picked the G4, not the biggest one. And this is the code. It just automatically put it on S3, made it available for the glue, exactly what you saw on the cursor or VS Code. The job detail, same name. You have type Spark because it's batch, it's not a streaming. You have the glue 5, which is the latest one that came out recently. Language is a Scala, but obviously you could do Python. Right? I just wanted to do a Scala, so you see also a Scala. Requested number of workers 20, and it's done. So if you go to the run, you can see it running now, right? You have 80 DPUs, and it's supposed to do what? It's supposed to go get a ratio of a PubMed that we already have on S3, embed them, put the embedding on a disk, right? If I click here, you will see probably these things are happening. Executors are being added. Now, if you do that with the EMR and Databricks, the startup is much longer. Sometimes it's 10 to 15 minutes. However, with the glue, it's around a minute because AWS Glue, if you don't know, is a serverless service, meaning that the time you ask for resources and the time you get it, it's usually between 20 seconds to 40 seconds, which makes it perfect if you need a job to run often, right? Let's say if you have to run a job every hour, you're not going to wait 20 minutes every time you launch a cluster, right? Yeah. So let's see how long it's going to take. But before that, I am going to also show you the examples we had. Like the text, a PDF to text that I talked about it, so you can see it in action. Obviously, you just have a very simple script to run it on Colab. You read 2 PDFs and just start the session. Here is your PDF to text. You set PDF to text, and that's it. You overwrite the binary file, point it to the place that you have all your PDFs, pipeline with the stages, transform. Everything is native. Everything is the same. And as you can see, it did extract everything. So this is the title, right? This is the page. And as here, as you can see, you have the height, width, content, exceptions, page number. These are the things that are very important when you are ingesting PDF. Now, do go check the rest of the, obviously the rest of the examples. We do have also a collection of everything Llama CPP related, starting with the model itself, generative models, your Llama, your Quen, your Mistral, and so on. And then you have GGF embeddings. Some people manage to quantize Nomic, BERT, these very popular embedding models to make them even smaller so they can run on a smaller machine with less memory requirements. And then you also have your typical AutoGGF vision model, which we talked about, and we've shown an example on Databricks. Again, very simple, end-to-end. This one is even telling you how to bring your own model in. Like here, it's going to go into Mozilla, the one that is on Hugging Face. So this is the quantized model. You can pick any of this GGF model, right? Here in this example, we picked the Q4, the 4-bit. Downloading that model, and again, preparing your setup for Colab, starting your session. You have your AutoGGF vision model. We have a lot of parameters. These are all coming from Llama CPP because we are natively supporting them. But the most two things that you have to be very important is that the chat template, you have the completion, the name of the column that is going to be outputted, and the input of that is your, I mean, we said caption document, but it's like a, I think it's a mistake that it says caption document. It seems like a commanding, but this is your instruction. I mean, what do you want from this picture? Like from this visual, what do you need, right? So because you have to say something, you have to ask something. Maybe it could be, I need you to write everything that you see in this document without hallucination. Don't add anything, don't remove anything. If there's a table, make it a markdown table, instructions like that. So depending on what you would do. And at the end, you have these, obviously, ImageNet pictures, and you will see, after some logs, the final result, which is like with the palace, it will talk about the image, depicts a large or, like ornate room with the high ceilings, yellow walls, etc., etc., right? So that's the example. Please do also go check these examples. In fact, we have a lot of examples. Please check them out. Let's go back to this. Well, done, right? Now, if I look into, so it took around 4 minutes to finish the job, right? If I could find the logs that belong to this job, hopefully, on here, that is, okay, that's not the one. I don't know exactly which, oh, this is one, okay. So you can see at the very beginning in our code, we left something. We said, let me go back to the code. Oh, we have a bunch of logs like, hello, etc. But once we took the PubMed data set, we said count, right? I'll zoom in a bit. I can't zoom in. So the PubMed that count, just to see how many documents did we do in 4 minutes, right? If I could find the CloudWatch, oh, there we go. So the total number of articles that we took, it was around 100,000, right? 100,000 abstracts that they are lengthy text, right? I mean, they're not full page, full text, but they're still big. They're not like one, they're usually are 2 paragraphs. We took those and we directly took them into BG embeddings and we just vectorized them. And we saved them on disk in 4 minutes. And it happened thanks to Spark NLP natively supporting distribution. It went over 20 nodes, right? We requested 20 nodes, as you can see here, 80 DPUs. And at the same time, thanks to AWS Glue being a serverless service, because it just launched all those 20 instances, all those 20 servers within 20 to 40 seconds. We didn't have to wait 15, 20 minutes like EMR or Databricks, right? That was nice. All right, so back to our presentation. That is the end. I would like to thank you, and I also want to give credit to some of the main maintainers of Spark NLP. Obviously, without the help of community and their contributions, whether opening feature requests, bug fixes, this library wouldn't be possible. So I would like to thank every single one of them who contributed to this library, especially the main maintainers. Please do go on the GitHub repo, start the repo, ask questions, report any bug, ask for feature requests, or just open a discussion and have a chat with us. Until the next webinar, thank you very much for your attention. Have a great day.